Okay. Good evening, everyone. So today we'll go through the doubt clearing, like the kind of some of the previous year questions and kind of summary of the lectures that was covered in this week. Uh, Again, so these are the kind of topics that were covered in this week's lecture series. So before going ahead, just confirm if I'm audible and the screen is visual. Someone please can.
Yes, yes.
Okay, thank you. So last time we started with some kind of intro to AI MLDL. What is the progress of AI MLDL? And we started with MP neuron and perceptron. That was the major focus last time, and perceptron learning algorithm. So that we saw last time, and how what's the proof of perceptron algorithm will converge every time. That also we saw, and we also discussed like some of perceptron cannot model every kind of logic functions, particularly exert functions cannot be modeled using perceptron that we saw because that is not linearly separable. So we kind of this week we'll kind of extend that discussion to a little bit more deeper context. Okay. Also, last time we introduced something called gradient descent, so that we will go through thoroughly this week. And variants of gradient descent we will see next week. Okay. So we have discussed last time also, but this week also again we'll discuss what is linearly separable Boolean function. Let me. Mhm. What are the linearly separable Boolean functions? What is network of perceptrons? So then we discussed only one perceptron, like a perceptron with one neuron. So today we'll discuss network of perceptrons. Then what is a sigmoid neuron? So last time, if you remember, we were discussing step function, right? Now we'll go beyond step function to some different functions. So starting with sigmoid function, so the neuron that kind of does the task of sigmoid function that is called sigmoid neuron. Then we go to like supervised learning setup. Again, we have discussed. We will discussed in a little deeper way. Then we'll go to gradient descent and do problem solving. Okay. So this is not going. Yeah. Huh. Okay. So last time we had discussed multiple Boolean functions like AND function, OR function, some functions with innovator neuron. Let's start with AND function. If we have two inputs, x1 and x2, x1, x2, and the output can be, let's say, represented by y. So what will be the output for different values of x1, x2? What are the possible values? Because we are saying these are Boolean in nature, it can take either 0 or 1. So possible values are 0, 0, 0, 1, 1, 0, 1, 1. Sorry, I was on mute. Yeah. Hello, am I audible?
Yes, yes.
If I'm going to mute, just someone you can unmute and tell me. Or maybe I was on mute. Okay. So last week we were discussing this AND function. You can mute now yourself. Last week we were discussing this AND function and when it will be one, when both inputs are one. Another case it will be zero. And if we try to draw it, the AND function in kind of two-dimensional plane. So this point belongs to 0, 0 input. This point, let's say, belongs to 1, 0 input. This point belongs to 0, 1 input. This point belongs to 1, 1 input. We know out of these 4 points, for this point only, the output will be 1. Others, the output are 0. So if we want to draw a linearly separable line to kind of segregate these 2 point these 4 points into two classes, we have a lot of option here. We can draw a lot of points to kind of clearly linearly separate these 4 points into two classes. But that was a problem in case of exer Boolean functions, as we discussed. We cannot. So here, this is the example for like kind of exer Boolean functions. So these two red dots, they represent class one, and these two blue dots, they represent class zero. We cannot clearly draw any linear line to separate these two classes. We need two linear lines here. Okay. So this is something one class of Boolean function that we call that is not linearly separable. The like when this all this MLI started, they were fine with this linearly separable function. They were able to kind of model whatever input was linearly separable, but the complexity of the data increased. Now we needed to kind of model non-linear data points, like they are not linearly separable. So in that case, like the goal of this course throughout will be like we'll try to tackle how when the complexity of data goes, like goes up, like the complexity of data goes up, how we can come up with more sophisticated models to kind of model them correctly. Correctly in the sense accuracy we have to preserve, like it should be as close to as one. Okay. We're discussing this perceptron network last time, right? In perceptron network, the input to the perceptron was, let's say, there are three inputs, something x1, x2, x3. There is one output. We know this is aggregator function, and there is some summation. There is another function here. So for first layer of the neuron is aggregator. It just sums up every input, and there is some function apply that is aggregation. Let's we can say as g of x. Then another function, that function we can choose on our own. Function of g of x will be the output at the output neuron set. And how we represent this in perceptron, it's like a summation of wi xi greater than some theta, greater than equal to some theta. If this holds, we say the output is one, right? So if we try to put that formulation and kind of model the exert function, what it will be, we know for these two input, the output will be one, other two input output will be zero here. So if you try to write, so W0 is the bias term, we know W0 plus W1 into 0 plus W2 into 0. Because the output is 0, it should be less than 0, right? So the theta here is 0. Theta is decided is 0. If the summation of WIXA is beyond 0, then output class will be 1. If it is less than 0, output class will be 0, right? So here the theta value is 0. And depending on that, we'll decide what will be the value of W1 and W2. So if you try to solve this, you'll kind of get these four equations, and you have to kind of replace any value for W0 and W1 that will uh, kind of satisfy all these four equations, right? Then you'll go, okay, this is the value of W0, W1, W2. But in this case, we cannot come up with a set of three values that will satisfy all these things, W0, W1, W2. We cannot come up with three proper values in the case of exert that will satisfy these four equations. So that's why, like, uh, it's a mathematical way to show that exert is not linearly separable. Diagrammatical, we can imagine and visualize why it is not linearly separable. And this is a mathematical way. How can we prove like exert is not linearly separable? Like just to understand, like let's consider. So what are some of the non-linearly separable functions? So this is one. This kind of data points also we have discussed last time. So if you see here in this plot particularly. Yeah, in this plot, I'm circling here. So the outer red circles, they let's say corresponding to class 0, inner blue plus they corresponding to class 1, let's say. We don't have a linear boundary to separate these two classes of points, right? So we have a non-linear boundary here. Okay? So can we come up with linear boundary to separate these 2 points? So all these things we'll discuss future post like future lectures of this course. Also, another kind of nonlinear function is when we have some noisy data points. So if you see majorly in this left side plot, majorly all the red points are on one side and the blue points are on other side. But there are some kind of noisy points we can say that maybe because of noise in the dataset collection or noise in the annotation, whatever noise in the measurement, multiple types of noise are possible. Because of some noise, some of the points on this side are kind of blue color and some are points on right side are red color. What does it mean by the color being red or blue? Like, let's say if the red color dots represent to class 1 and blue color dots represent to class 0, during annotation, maybe because of some noise, these 3 points were annotated as class 0, even if they should be class 1. So this kind of noise is possible in the data creation step. So now model will get confused. Okay, majorly the points are points on the lower side are class 1, but there are some points that are also class 0, because model only sees the input data that is given to it. Model doesn't know whether the annotation was right or wrong, right? So because of some annotations also, non-linearity might come up. So how do we tackle these problems also, that we'll discuss. So these are the kind of, so this is intended non-linearity. This plot I am again highlighting again. This is intended non-linearity. This is not intended non-linearity. So how we'll address all these kinds of problem we'll discuss. Again, now coming to networks of perceptron. I hope you understood what is linearly separable and what is non-linearly separable. If there is any doubt, you can unmute and ask. Okay, what is network of perceptron now? So again, as I was discussing, we discussed only perceptron with respect to one neuron last time. Right? There are a bunch of inputs, maybe one bias input, others are feature inputs, and there is one output, and this works as aggregator, then followed by a function. That function we can choose. So this single neuron is not enough to model any complex functions. So it can only um, kind of model some simple functions like step function, maybe some one sigma function, one sine function, like one kind of function it can model. To come because but the input output relationship between the data points that is present in the real world scenario, the relationship between this function, the nature of this function generally is not that very simple. So to model that, we need some complex architecture or complex. We need to capture this complex relationship between input and output. For that, we need more neurons. Just one neuron will not be sufficient. So that to achieve that, people started with like having multiple perceptron neurons in a single layer. So we can call this as a layer. So going ahead, maybe next week or next to next week, we will discuss something called multiple layers. What is multiple layer? So in one layer, we'll have multiple neurons. Another layer, we'll have multiple neurons. Maybe same number of neurons or less number of neurons. So it's like kind of we can say this is layer 1, this is layer 2, layer 3. So but we like initially we have not reached there. We started with like just having one layer and multiple neurons and wanted to see how what kind of complexity we can capture in terms of input and output relationship. Let's say last time we were trying with three inputs, but just one neuron we were trying with, right? So here we are seeing like only those three inputs have been used, but the number of neurons are increased. So now we'll have kind of much more functionality to learn about these three inputs. Like we can say this neuron can learn one kind of relationship between x1, x2, x3. These three neuron can learn another kind of functionality or kind of interactions between x1, x2, x3. This neuron can learn some other interaction between x1, x2, x3. When I say interactions between x1, x2, x3, how they are related with respect to the output. We know output for us is y. How y is related, like how y changes with respect to change in x1 and x2 and x3 individual or in combinations. So that change can be represented through some function. And our like hypothesis is not a single function can capture that series of changes. Some type of changes can be captured by one function, some type of changes can be captured by other type of function, right? So that's what we want to like kind of tackle through multiple neurons, right? So again, so if we try to mathematically present this network, how it will be. So last time we presented this network by summation of wi xi greater than theta, right? Here it's the same thing. Only change is now for the output we have one this is one layer, but the output layer is this neuron only, right? These neurons can be called as the neurons from the intermediate layer. This can be called as output layer neuron. Output layer neuron. These neurons can be called as intermediate layer neurons, right? So what we have studied till now, that can be mapped to output layer neuron. So for output layer, you can consider these are the 8 inputs going in, like summation of and these are the kind of weights. W1, W2, W3 are the weights corresponding to that, and we can see like whatever inputs, or we can represent output of these perceptrons as HI, WI greater than equal to 6. But what what is H1? Let's say what is H1, H2? Like what are the outputs going from individual perceptron in the network of perceptron? For that, we have to compute again summation of Wi xi. Here the input is xi. Here the input was for the output neuron, input was hi. Okay. So this WA again, I am mentioning WA, but they're different W. So you can say this as W1I and these are kind of W0I, like zeroth layer Ws and first layer Ws, like that. And so these are the kind of the way we present them mathematically. So there were many like kind of theoretical work around this. So okay, for 3 inputs, you need a kind of 2 to the per n perceptrons, 2 to the per n perceptrons, and on output layer of 1 perceptron. In combination, 2 to the n plus 1 perceptron that can model any types of function, like any kinds of relationship between x and y. For n inputs, it's 2 to the power n. 3 inputs, it will be 2 to the power 3 plus 1, 9 neurons. Layer, you need 2 to the power n, like 8 neurons, and output layer 1 neuron, like that. So again, I'm not going to the proofs of that. You can go through the lecture. But in terms of overall understanding, if you have any doubt, I can explain. Now we'll come to something beyond just the step function. So till now we have been discussing about this step function only, like summation of wi xi greater than theta. So this step function only we have been discussing till now. Yeah, so we'll go beyond step function and see what kind of functions or what kind of relationship between input and output we can capture. Yeah. Again, this was the step function we discussed last time. First, diversity we learn is like variant we learn is like that is a sigmoid function or the sigmoid neuron. Its other name is logistic neuron also. So what is the function of what is the logistic function equation? 1/1 plus e to the minus wx. So if x is the input, y will be, so f of x is always y, right? So we know this from our elementary mathematics. So y will be 1/1 plus e to the power wx minus wx. So you change value here on x, or you will get different y value. So this is the simple sigmoid function. So if we try to plot this, what is the nature of this step function we plotted last time and we saw, right? After some value, after the theta, so whatever the theta, it can be theta, can be 0, 1, 2, 3, whatever, it will just jump. The class will be corresponding to 1. Before theta, it will be class will be corresponding to 0. The problem with step function was there is this direct jump here, right? So when we go ahead and learn gradient descent, we'll realize we need a differentiable function here. So this perceptron has two parts. One is aggregator and there is another function. So aggregator is just addition, right? That is differentiable. This function has to be also differentiable so that when we'll do the backpropagation, we can do backpropagation neatly. If this function is not differentiable, that creates a problem in the backpropagation. So we wanted to kind of create a smoother version of this step function that you can see this sigmoid is kind of a smoother version of the step function. There is no sudden switch. The curve is kind of smoother as compared to the this step function. Because of this jump, we don't know what will be the different, like the value of differentiation at this point particularly. But there is no such complex point here in the sigmoid plot. So now, but how will it decide this theta, like class one, class zero? Here we knew we can come up with some theta that where the jump will happen, and that will give us decision boundary for class one and class zero. Here also we can decide some theta. Generally, the theta that we decide is like 0.5. So we apply this function and get the value y. So what will the range of y? Y will be between 0 to 1, both inclusive. Okay. So if the value of y is beyond 0.5, we'll say this is class 1. Class 1 is greater than, I'll rewrite this maybe. Greater than 0.5, greater than equal to 0.5, we can say class 1, and less than 0.5 is class 0. Again, this is the mostly practice. No, I mean, in practical case, most of the times we use this threshold, but depending on the like task on hand, kind of the data distribution, we can also change this threshold. Yeah, the major concern was this was not differentiable. Now this is differentiable. So again, we'll discuss this kind of functions in detail also in next class. Still, I'll tell you what will be the derivative. So this dash is the representation of derivative, as we all know. What will be the derivative of sigmoid function? This will be we generally represent sigmoid as this sigma. Sigma is now what will the derivative of this sigma into 1 minus sigma. So you can try, like I am not explaining, I am not expanding this in this class. Next class I will explain, but you can try out at home why it will be derivative of sigma equal to sigma into 1 minus sigma. This is the simple differentiation we have learned in our elementary. So I'll discuss next class, but we can give it a try first. Now we got some basic components to understand supervised learning and how to understand how supervised learning works. First thing is we understood neuron, we understood pattern, like kind of network of neurons. We understood this aggregation function has to be differentiable, and there is a function after aggregation that has to be differentiable. One variation of differentiable function also is so. Now let's combine everything and gather all the components to understand supervised learning setup. So in supervised learning setup, what happened? So if you remember last time I discussed, there are three major kinds of machine learning problem. One is supervised, another is kind of unsupervised. Here I discussed clustering, just to give you idea how unsupervised works. Another is semi-supervised. So majorly during the course we'll see supervised methods. Very few occurrences we'll see unsupervised methods, and semi-supervised. We end with some of the semi-supervised applications and algorithms. So, but major we'll be discussing only supervised setup. All the kind of basic mathematics and the like understanding of MLDL will be done through supervised algorithms only. Okay, so in supervised setup, what happens? We have a set of inputs like x1, x2, x3 up to xn. So these inputs can be of any types. This can be tabular data, this can be kind of text, this can be image, this can be video, anything. For every input, we have a corresponding y. So this is x input data, and this is y. And for every input data point, we will have a corresponding y label. So again, this y label, if it is binary nature, it can be 0, 1. If it is kind of multi-class problem, then it can be of 0, 1, 2, 3, whatever, depending on the number of classes done. Let's say where the task is to classify digits. If this digit is the image corresponding to which digit. We know there are 10 digits, right? So the problem is like a 10 class problem. So possible values for each y will be 0 to 9 here. If it is just sentiment classification and we are focused on positive and negative sentiment, the possible class is only 0 or 1, 0 or 1. So depending on the task at hand, the range of values for y will change. Right. So the example given here in the like the lecture series is like kind of sentiment classification on the movie name or movie data. So given is movie name, output will be whether you like the movie or dislike the movie. So there is a binary class problem. And if you give a careful thought, this sigma function we can use when the nature of the problem, the nature of the task is binary in nature. You have to predict whether the input is corresponding to one class or the other class, because we have only one threshold here that can help us classifying into one class or other class. Okay? So that's why we are able to use sigma function here, because we have to decide whether the movie was the person liked the movie or disliked the movie, right? So it's a two class problem. So we'll see like in future what other functions are available that can help us to model multi-class problems. Right. So here, when we are thinking about a complete supervised setup, first thing we need to know is what is the data we're working with. Then what will be the modeling? Modeling is like what are the function we are using. In case of perceptron, what is the function? We know this aggregation is fixed. The modeling decision will be coming here. What will be the function that will be done after aggregation? We're not going to multi-layer perceptron again, I'm saying. So when we'll go to multi-layer perceptron, we have to decide how many layers, how many neurons per layers, all these things. So we are working with now single layer perceptron, just multiple neurons at a single layer and one output layer. So there we have only few design choices, like only one design choice. What will be the function after aggregation in the perceptron? The parameters are the W. Again, the number of W's will depend on the number of input features. Like here we are, let's say three input features and what is the example? Here we have three input features and one perceptor. So we had like three W's and one bias, 3+1. So if we have multiple input, sorry, neurons, then we know how many W's we'll have. 2 to the power n plus 1 perceptrons, meaning those many W's will have. I mean, not those many W's, like 2 to the power n plus 1 perceptrons, and each perceptron require 3 W's because there are three inputs, right? 3 into 2 to the power n plus 1. Maybe not very much accurate. I will explain it again. So in inner layer, so intermediate layer has 2 to the power inner layer has 2 to the power n neurons, and every neuron requires 3 W's. That is, if we are forgetting the bias term. I'm just forgetting the bias term. I'm not using the bias term now. Without using the bias term, 3 W's corresponding to each inner neuron, like intermediate neuron, and output neuron. This neuron requires 8 W values, right? So these are the those many number of W. So this is while we're designing kind of any supervised in the designing the model in any supervised setup, we need to inherently know how many parameters you are using. So we'll know the significance of this in future lectures. Why we need to know how many parameters we are using. So some concepts of overfitting, underfitting, that when we'll be discussing those concepts, we'll need to know how many parameters we're using, whether we have to reduce the number of parameters or to increase the number of parameters. That significance will come there. So at least we should know how we're measuring the number of parameters. Given a model, given set of inputs, how many number of parameters are involved in this complete setup, that we have to know. So in this perceptron, I hope I could explain you clearly, like the number of three neurons, if there are three inputs, three W's for every intermediate neuron, and how depending on the number of intermediate neuron, the number of W's for the output layer will also change. Right. Now then, okay, so we designed the W's, like how many W's will be there and what will be the function. Now how we'll update the W's, because when we start the learning, we start with some initial random W values, as I discussed through multiple plots last time, right? So we don't know what's the optimal W. So for that we have to we have to follow some algorithm that is called learning algorithm that will start with gradient descent this time. How gradient descent will help us to find optimal W for the given input output pair. Again, if the input output pair changes, that set of W that we have learned might not work, right? So whatever W we learn through gradient descent will be best fit for our input output pair that is given to us in this learning setup. And then coming to how do like we'll kind of learn the W's through gradient descent. Okay, that is fine. But how do we know whatever W's we are learning if that is good or bad? For that, we have a loss function. The loss function will give us measure कि current set of W is good or bad, whether we have to do the gradient descent step further or not. If it is bad, we'll continue doing the gradient descent. If it is good, we'll stop the gradient descent, right? So for that, different loss functions are there. There is a kind of this is a squared loss function, as we say, square loss function. There is something called absolute loss function also. Absolute loss function. So absolute loss function, how it will be computing the loss? L of W will be summation of I equal to 1 to n yi hat minus yi only. So there is no square term here. As you see here, it is being squared. So the problem with this loss function is, uh, let's say for one particular input, one instance I am only talking about ground truth. Here the ground truth is yi. The prediction is yi hat here, right? So if the ground truth was, let's say, 1, in one iteration of the algorithm, it predicted, let's discuss two data points, not one data point. There are two data points, both yi1 and yi2. Both has ground truth value 1 each. And one iteration of the algorithm, what happened? yi1 hat is predicted to be 0.7. Because we are using sigmoid function, the value can vary from 0 to 1, as we know. These are floating point numbers, so it can take any value from 0 to 1. And let's say if in one iteration it predicted 0.7. In the same iteration for yi2, it predicted, let's say, 1.3. It cannot predict 1.3 if it is sigmoid. Let's say it's not sigmoid, it's some other function that just gives us a linear output. Let's say it predicted 1.3 here. So if we're using this absolute loss function, what will happen? We'll just find the difference. Here, what will be the difference? 1 minus 0.3 is 0.7 is 0.3. And here it will be 1 minus 1.3 is minus 0.3. If you try to see like in combination all these data points, how are they are performing, the summation will be 0. This will give us a false impression that the learning is perfect. There is no loss because the summation of all the loss values are 0. But if you use the squared loss function, you will actually see there is some significant loss, right? So that's why the squared loss function is better than the absolute loss function, right? I hope this is clear. Again, this is a very important concept. Why squared loss function is majorly used as compared to absolute loss function. uh, we'll be frequently using this concept going on. So if you're not understanding now, feel free to ask me. Yeah, so this is the complete setup. Now in detail, we'll understand the gradient descent algorithm. What happens in gradient descent? Again, so this plot we have seen last time also. So this is, let's say, the plot corresponding to the W values. So what exactly this plot shows? How the loss changes. So this y-axis corresponding to loss, this x-axis corresponding to W. So in with change in W, how the loss changes. we start with some random W. Let's say we started with this W value. This W value is here, whatever W1. Or let's say we started with some W value here. So let's say that is WJ, WI, this is WZ. We can start with any of these W's. Like the range is very diverse. But our target is, let's say this is the global minimum. Our target is to reach here. Okay. So if the loss, you can see here, the loss is the minimum loss. This loss we want to achieve. Let's say we started with this loss, right? How will start, like starting from here, how will we reach to this loss? Let's say we cannot reach this loss, so we're happy with reaching this loss also. How will we reach this loss also? So what's the strategy of using, so to reach this loss, we have to come to this W, right? So what is the strategy of changing W so that we'll come to this point, from starting from this point to this point, so that the corresponding loss value will be kind of less as compared to the point we started with, right? Yeah. So if you're starting in this plot, if you're starting with this W value, and let's say what will be the slope here? The slope here is in this direction, and if you're starting here, let's say the slope here will be in this direction. Again, this slope and the direction slopes, these are coming from the elementary mathematics completely. This is nothing new here. The way we have understood the slope, this is the same slope here, like learning here. There is no change in the meaning of slope we have learned from our elementary mathematics, right? So if we're starting from this point, the direction of the slope is upwards, right? But we have to come downward, right? We have to come this way, in the opposite direction. Here also, if you see, we're starting, the direction of slope is this way, but we have to come downwards. So every time to reach the optimal point, we have to come backwards to reach the optimal point, because this is a minimization problem. We have to minimize the loss. In case of maximization problem that I was discussing last time, we have to go like the nature of the curve will be like this. We have to reach here starting from here. There we have to add. There we don't need to subtract because we have to go up. Here we have to go down from the starting point. So that's why we have to every time subtract. Like if you are not reaching this point, we have to, wherever we are, we have to subtract. Right. So that was the intuition behind the gradient descent. That's why we call this as descent. Gradient descent. So what will be the parameter update rule for a particular for timestamp t plus 1? We take the value that was there in the previous iteration wt minus eta into delta wt. So what was the slope here at the wt? So how much changes that should be happening? That is the delta wt. So changes with respect to what? With respect to L. So what is delta wt? Del of L by del w. At tth timestamp, whatever w value was there, with small change in that w value, how much L is changing? That is being represented by delta wt. And if you have a bias term, also correspondingly we can understand with small change in bias, how the loss value is changing here. That is being represented by delta del b. So if we reach this point, what will be the value corresponding to delta WT and delta B? You can assume, because there is no oscillation here anymore at this point. With small change in W also, there will not be any change in L. So delta WT and delta B will come to 0. You take any, so there is a plot curve going on, and there is a flattened region. Because y-axis is loss here, right? Y-axis corresponding to loss. In this region, you change W value how much? There is no change in loss. So similar thing will happen in the the minimum point. With small change in W value, there will not be change in L. So there will stop our gradient descent algorithm. We will not iterate it further. Okay? So that's the goal. We have to reach a point where after changing the values of W and B slightly, there will not be any change in value of loss. We don't know if every time we will reach optimum L, this is the optimum N. So that is called global minima. This is something called global minima. This is called local minimum. So all again, this depends on the initialization W value. If we initialize with this, it is easier to reach at global minimum. But if we initialize with this, it's not very easier to reach at global minimum. We'll get stuck at local minima because our algorithm will figure out, okay, once we have reached this point, after slight change in this value, loss value is not changing, we'll stop the iteration. We'll go out of computation of the algorithm, right? But it's fine. We are like in machine learning setup. Many of the times we'll converge at local minima, and we're happy with that. We don't need to reach global minimum every time. The again this has some significance in the discussion of overfitting or underfitting. And keep these things in mind. We'll discuss it again while discussing overfitting and underfitting. Why every time you don't need to reach global minima, and we're fine with reaching local minimum. Okay, so these are the kind of concepts that were covered during this week's lecture. I'll just wait for 1 or 2 minutes if you have any doubt. Otherwise, we'll start with some previous year problems. Feel free to unmute and ask if you have any doubt.
Hello.
Yeah.
Yes. Can we solve this global minimum problem by taking different initial values?
Yes, by taking different initial values, we can solve the global minimum problem. So again, now because initially we don't know the nature of this loss function, it's like kind of hit and trial. Like we can 1 second. Knocking at the door. What I think, because we don't know the exact nature of this plot, we cannot say what will be the best initial W value to reach the global minimum. But there are some algorithms that try to figure out key depending on the kind of architecture or the number of parameters and the number of so the type of nonlinear function. Here the nonlinear function is sigmoid. Depending on the number of neurons and number type of what will be the best value. But again, they are empirical in the sense like experimental. Sometimes they work well, sometimes they don't work well. But we, with guarantee, we can say we will reach the local minimum, and that will suffice for us.
Okay.
So you can imagine, like, if you're starting from this point, 1 second, let me. So if you're starting from this point, because the gradient is this side again, side and everything backwards, will reach this point easily than this point, this local minimum. Also here, if you start from here, yeah, there was some network issue. I think I'm audible. Yeah, anyone has any other doubt?
So this mathematics part is essential, like this differentiation and um,
Yeah, to get the optimal W, this part is essential because we need to know how much change we have
okay,
find. So this is some W value, right? We started it with this WI, and let's say this is W optimal. To know this, what is the value of W optimal, we need to know how much change every time we have to do. This change without differentiation, we cannot find how much change we have to do. Once we have found how much change we have to do, we have to make the change also actually. That making change is being represented by this minus here. How much change that is being represented by delta W. just two mathematical component here. How much change we have to do, and then perform the change.
So this delta WT and what is this eta?
Okay, eta I didn't explain. So this eta is something called learning rate.
Okay.
Again, so I skipped this now because in detail we'll discuss this learning rate next class. So what this tells us, like we know this is the delta WT. So I'll plot it again. This is W, this is L. So let's say this is the curve. There are 2 points let's discuss. Let's if we are starting here or we are at here at one point Wi, or maybe we are at this point or at some other time, that is Wj. Wi, Wj. So if you are at Wi, if we try to compute del L with respect to del Wi, and another scenario we are computing del L by del Wj. So what will happen? What will be the relationship between these two values? Whether this will be higher or whether this will be higher, we don't know. But the exact values we don't know, but the relationship we know. Right? How do we know the relationship? Because here the slope is like uh, the inclination is higher here. So with small change in W, so where we're changing the W on x-axis, right? You can see on the x-axis with we started with here. With small change in W, there will be a large change in L here, as compared to with small change in W here, how much change in L happening here. You can just take any curve like this and check the value yourself also. You change the W here a little bit, and how much L is changing here when we initialize with this, and how much that change is happening when we initialize with this, right? So generally, because the inclination is higher, where the inclination is higher, the change will be larger here. The actual relationship will be this delta W at del W but at Wi will be higher as compared to del W at Wj, because the inclination is higher here, the slope is higher here. So that's the motivation behind learning rate. If the slope will be higher, sometimes it might so happen the loss plots are like this. Here the slopes are really high. So del L by del W will be really high. So because of that, when we change like this delta, this is represented by delta WT, right? Delta W2 will be really high. When we change, what might happen? The next iteration, the W will come here. So this will kind of jump here to here to here. It will jump. To reduce that jump, that oscillation, that we call that oscillation effect. To reduce that oscillation effect, we multiply on with something called learning rate. So if you're not multiplying anything, we're completely considering delta W. Let's say 1 into delta W, right? If we know the oscillations are really high, we can reduce that oscillation by multiplying, let's say some uh, 1 second. So we can reduce the oscillation by multiplying the learning rate. Like if we let's say multiply, if the slope is this steep, like this plot, slope is very steep, so delta W will be really high. So if we multiply by let's say 0.1 and 0.2, instead of reaching this point, we'll reach let's say this point, right? So that's the importance of learning rate, like how much importance you have to give to this delta W. And sometimes it might so happen the nature of plot are very kind of shallow. The delta W will be very small, but we want to take big steps. We want to jump big steps. There we can have higher delta eta values, the learning rate. There we can have let's say learning rate of 1 or 2. So without multiplying learning rate, if we just consider the delta W, we might go from here to here. But if we multiply some big learning rate, we can go from here to here. So again, that's experimental, depending on the stages of training. Like if you're starting with some initial stage, we know the delta value will be really higher. So we'll use low learning rate. Going on, we know we are coming closer to this local minima. We don't need to make bigger jumps. Either we can make the learning rate even lower or larger. That depends on the training stages. We'll discuss what are the strategies of changing this learning rate in next class only in detail.
Thank you. I have a
Any other
very
doubt?
basic, yeah, a
Pardon?
very, I have a very basic question. Like when
Mm-hmm.
we write the
Mm-hmm.
delta is a triangle now with the base.
Yeah, yeah,
Uh,
yeah. Like reverse triangle, you can say.
yeah, so this is opposite of delta something. I mean, this is
Uh,
inverse triangle. This triangle is
yeah,
inverse.
yeah. Delta symbol is this only, inverse triangle.
Okay.
And this is other term, related term is del. Del is like partial differences. So these are some of the basic mathematics you need to know, like partial differentiation, to understand this complete gradient descent or complete algorithms.
Okay.
I think
Thank
some
you.
of the basic mathematics I explained last time, that you have to go through, like what is vector, what is vector space. I don't remember if I discussed this partial differentiation little bit. You need to know to understand different nonlinear functions. So we are discussing today only sigma. Going ahead, we will be discussing 4 or 5 different functions. So to understand them, their nature, why one is better than other or one is not better than other. To understand that, we just the differentiation and partial differentiation we need to know. If you need to brush up your basics on that, feel free to do it from some other source.
Okay. Thank you.
If time permits, I can explain through some example, but yeah, let me finish first. Any other doubt
No.
from anyone else? Okay, let me go to the previous year problems. Okay, so let's read every problem in detail first, then we'll see the options. So first question says, uh, the first question says, squared error function is preferred over simple difference between actual and predicted value. This we discussed. The squared error function is L equal to summation of I y hat minus y whole square. This is the squared error. Simple difference is like summation of I y hat minus y. There is no square involved here. To identify the appropriate reason for this statement, why it is being preferred. Square blows up the error. Square doesn't blow up the error, so that's not the problem. In second case, positive negative errors cancel out each other. So that we discussed with that we saw with one example when it was predicting either 0.7 or 1.3, right? So this is the right option. It is not differentiable. A square is differentiable, and a statement cannot. So yeah, so the option B is right here. The second question says, pick out the parameter that enables the model to learn the given data for the given function. So data is x and y only. So the given there is nothing else given data. And the function is y hat f of x equal to 1 by 1 plus e to the power minus w transpose x. Okay. Y hat is the function f of x. So we know what is the parameter. The parameter involved is w, option A. So when we say we're learning a model, we're learning these w values. X and y are fixed. We're not that is given to us. Learning model is about learning those W values there that is there in the model. And what are the W values? How many W values are there? That is again design choice. That when we are deciding a supervised setup, we decide in the modeling stage how many W values will be there. Yeah. So identify the function that cannot be used in a machine learning model. Okay. So when we say something cannot be used in a machine learning model. So machine learning model, again, the way I was saying, the modeling meaning there is some W value involved, like we have to learn some W value because apart from that, there are two more components, X and Y, that is given to us. We are not learning anything. So here, if you see option C, it doesn't have any W value. So we're not learning anything here. So that's not a machine learning model. So other three things, they may be right or wrong, but we're learning something. So they can be considered as machine learning model. We don't know if they're very good model for the given X and Y, but they're machine learning models. So
I have a query here.
yeah,
So W is the weight, na weight.
yeah.
So initially, when we were doing this MP neuron, that
Mm-hmm.
was not having any W.
NP neuron is like very primitive model, you can say. So that's the only exception.
So okay, but it was
MP,
also
MP neuron
learning.
is the only exception that doesn't have any W, but any other machine learning model you take that require a W.
Okay.
So that is like kind of pre machine learning era where nothing was there. They just wanted to see the brain behavior. They came up with MP neuron.
Okay.
Okay. What's the next question? The condition for the new loss function to be less than current loss is this also okay. If you have gone through the week's lecture, this was taught as a proof for gradient descent. So condition is this is the current loss L whatever we have and the direction of this W here, that is U. Uh, our goal is like this U transpose L should be less than zero, meaning the cosine. And so we how do we measure whether it will be less than zero? We measure it through like cosine similarity. We take the U transpose L. This will give us the cosine angle between U and L value. It has to be less than zero. So what is the direction of U with respect to gradient for which the decrease of loss is maximum? So as we was discussing, like again intuitively I'm saying I'm not going to the proof now. So this is the loss curve, let's say. This is the gradient. When when kind of the loss decrease will be maximum, when we'll going in the exact opposite direction. Right? So if you are going, let's say some other angle, will reduce the loss, but not as much as when we're going exactly opposite, that is 180 degree. So that is the maximum reduction. Why it is happening? You can simply understand from the nature of the cos. Cos 180 degree is minus 1, right? So if you want to find cos angle between U and L theta, if it is minus, sorry, if it is 180 only, the reduction will be like minus 1 into what is the delta value. Okay. So here the reduction will be the highest. Any other value you take between 90 to 180, it will be some floating point number, 0 minus 0.7 or something like some floating point number it will be. The reduction will be only highest if you're going in the opposite direction. So that's why we subtract. That's the intuition behind subtracting here. W equal to W minus eta into delta W. So right option will be 180. Next question, given that you have n inputs, how many Boolean functions can be designed? Okay, so it's asking about number of Boolean functions, right? Let's take example of two inputs, x1 and x2. So if the nature of the x1 and x2 are a kind of binary, there are 4 combinations, right? Sorry, 1 0 1 1. Now the what question is asking how many Boolean functions we can design. So this is the kind of different inputs we could come up with. These are the 4 possibility of input pairs. To get the function, each can take again 0 or 1 value, right? So everything sometimes it will take all will take 0, sometimes all will take 1, sometimes some of them will take 0 and 1. So for every input and output, there are 2 possibilities. Right. So how many input possibilities we could get? That is 2 to the power n, if n number of inputs are there. And for every input, again, we have 2 possibilities, right? So if 2 to the power n can be represented by, let's say, some L value. So for every L value, there are 2 possibilities. So total, there are how many possibilities? 2 to the power L. That is 2 to the power 2 to the power n. So for n inputs, take in terms of y, either they can take 0 0 0 0 or 0 1 0 0 0 0 1 0. There are many possible values they can take, right? We don't know which Boolean function they represent, whether they are one of the standard and or XOR, or may not be. There are some other Boolean functions that they are not standard that standard function that we use, but there are some Boolean relationship, right? So every y value has 2 possibilities, 0 and 1. Every y value. So there are 2 to the power n inputs, and every input will have 2 possibilities. So that's why 2 to the power 2 to the power n. So option should be 1. Okay. Now coming to question 6. Which of the following is true for a multi-layer perceptron model? So multi-layer perceptron, again, in network of perceptron I was discussing, there is one only one intermediate layer. In multi-layer perceptron we can have multiple neurons, multiple layers, and every layer will have multiple neurons, or not necessarily equal number of neurons. Statement 1 says any Boolean function can be represented by a single hidden layer. Okay, so let's see so we have to see which one is true, right? We discussed like only one neuron cannot represent all Boolean functions. Exception was XOR. But if we have a network of neurons, as we discussed, so okay, while discussing this, maybe I forgot to mention. So this is during studying when we were studying the history of AI, we studied something called that phrase was universal approximation theorem, right? Universal approximation theorem. If you are not able to recall, you can go back and see the lecture. Sorry, the recorded video. Approximation theorem. So this theorem, what it says, you take this many neurons, this many 2 to the power n perceptrons for n inputs in one layer. It can model any Boolean function. So there is a proof for that. That is called the concept is called universal approximation theorem. It can approximate any Boolean function given n inputs if you have 2 to the power n number of neurons in the intermediate layer. Okay. So going by that theorem, yes, XOR can be any Boolean function can be represented by a single hidden layer in a multi-layer perceptron model. Only catch here is you need that exponential number of neurons, exponential with respect to the number of inputs. Statement 2 says the number of perceptrons for this hidden layer is n square. It's not n square, it's 2 to the power n. So only statement 1 is true. Where n is number of classes, not number of classes, n is number of inputs. Number of inputs. Okay. Next question. Suppose the number of neurons Yeah.
What is number of
Yeah.
classes?
Yeah, so number of classes is that depends on this y value. So what is y? So here we in setup we discuss like the problem at hand is given a movie whether you like or dislike. So like or dislike there are two values, right? Two classes here. As I was discussing, there can be another setup where you have given images of digits. You have to say which digit this image corresponding to 0 or 1 or 2 or 9 up to 10 possible values are there. So that
Okay,
there the number of classes will be 10.
okay, fine.
Let's say you are doing some image classification, your focus is on animals, let's say 5 different animals, cat, dog, tiger, lion, like that. The number of classes is 5, like that.
Okay.
Again, till now, whatever we have studied, we can do only binary classification. If y takes either 0 or 1. How to do multi-class classification, we'll be studying in third or fourth or fifth lecture, not third lecture. Yeah, so we're now at seventh question. Suppose the number of neurons in the input layer is 9. Yeah, input layer is 9. Consecutive hidden layer is 5. So there are two different layers now, input layer and the hidden layer. Pick out the maximum number of connections that can exist from input layer to the hidden layer. Okay, input layer has 9 neurons. Let me draw 9 neurons here. 1, 2, 3, 4, 5, 6, 7, 8, 9. And the hidden layer has 5 neurons, right? So in MLP, what happens? Every neuron in the layer L minus 1 layer will be connected to every other neuron in the Lth layer. Forget about the term input and hidden here. So this is the concept for every consecutive layers. So neuron from L minus 1th layer will be connected to the every neuron in the Lth layer, right? So this is not for only one neuron, for every neuron. So how many connections for one neuron in the L minus 1? 5 connections, because there are 5 neurons in the Lth layer. So how many neurons here? 9 neurons. So 9 into 5 equal to 45. So 45 connections will be there. Okay. Next question. Which of the following results when the value of b is changed in the sigmoid function given below? Okay, so this is the sigmoid function given to us. So it is asking when b will change, what will happen? Let's see the options. First option says value of x at which transition occurs. Okay, so it's asking what's the significance of bias here, right? So this is sigmoid, right? We know the sigmoid plot is like this. Uh, the sigmoid plot that was taught here is this, or maybe another kind of sigmoid can be this also. To start from negative, go to positive, at 0.5. There can be multiple nature of sigmoid, but when the plot will be this, when the plot will be this, how it is decided? There the concept of this bias will come into picture, right? Am I audible? Seems to be some
Yes, you
network
are
issue.
audible.
Yes,
Okay, okay,
yes.
okay. Thank you, thank you. So what happens with this change in v value? The this shifting, whether we are starting from this 0 point or we are starting from b, that will depend on how what is the value of this b, right? Where this transition occurs, that will like this b will decide us, give us like decision where the this transition is happening. Okay, so if the b's value is 0, this is the plot that was taught to us. If b something else, either will start from here or will start from here, depending on the value of b. You can like kind of in Google also you can try out one by one plus e to the power. Some x plus 2, x plus 3, we'll see, or x minus 2. So if b is negative, what will happen, and b is positive, what will happen? You can just visualize those plots. So the answer is the value of x at which the transition occurs. Next question.
In the previous question, option 4, that can't be right. The transition point can be found based on bias.
So here the transition point. So when we say transition point, here two things are involved, right? Like one is W and W or B. W or B. Okay, one second. W or sorry, not W and B. Uh, so this is X here, input X, and this is Y, right? So when we're saying transition point for x axis or the y axis, that is not decided here. So there are two transition points, if you can see. One here, the transition point for y axis, and this is the transition point for x axis where we're starting. Okay. So clearly, like the value of W will give us the transition point for y-axis, whether it is what do we mean by transition point for y-axis? Whether it is very steep, whether it is very smooth, whether it is completely flattened. This is the transition point of y-axis. And where you are having the starting point, this value, whether you are starting here, or starting here, this is called the transition point of the x. That is not clearly mentioned here, but whether it is x or y. So this option is not completely true. Transition happens, it helps us deciding the transition, but on which axis? W helps us deciding the transition on y-axis. B helps us deciding the transition on x-axis.
Okay,
Right?
thank you.
Again, you can write in Google. You just type plot of 1 plus e to the power 3x plus 4. You fix the value 4b and change the value 3 to minus 3, 10. You see how steeper it is going, how flattened it is going. And you can change fix value of w and change the value of b and see which transition happens. Yeah. Consider a single perceptron that takes a single input.
You are
Pardon?
saying we can see on Google. You mean in Google Colab with coding?
No. Just Google search. Google search. Just type plot for 1 plus 1 by 1 plus e to the power minus x or something. It
Okay.
will give you the plot. The way we're
Okay.
searching, let's say we're searching Olympics, searching like this, right? We're typing Olympics. There you can type like plot for some function. You can define the write down the function. It will give you the plot.
Okay.
If you know the Colab, if you know Python, all these things, you can anyway you can do it, and that's also possible. If you don't know the Colab or Python anything, you can search on Google also. Okay, so next question is consider a single perceptron that takes single input. And what is the significance of this? Whether the student has passed the internal assessment. Okay, so this is making one decision whether the student has passed internal assessment or not. So this is a binary problem whether 0 and 1, pass 1 or not pass 0, like that. Perceptron predicts if the student can pass the end semester exam. Now the bias is minus 0.5, bias term is minus 0.5, W1 is 1. What will be the prediction of if the output value is 0.51 and 0.49? So what will be the function here? Let's say first, we know B is minus 0.5, and our equation is Wi xi greater than theta. All right. So here, what is Wi? Wi is I'll just 1 into some xi, right? 1 into xi greater than, sorry, 1 into xi plus w0 into 1. That we know, like we can do w0 into 1 and greater than equal to 0. If we are doing w0, we are taking theta on the left side. We can make theta 0 on the right hand side, because as we discussed last time, wixi greater than equal to theta. Now we are making wixi minus theta greater than equal to 0, and this minus theta we can represent it as w0 with corresponding x as 1. Here the x as 1. For every other thing we are given input xi, right? Then the thresholding here will be on the right side will be 0. So what it is saying, if the output values are 0.51 and 0.49, w0 we know x1 minus 0.5, bias is 0.5, and w1 is 1. What will the prediction if the out?
Sir, you are not audible.
Hello, am I audible?
Yes, sir.
Yes, now
Okay.
you are
Thank you. There's some issue with network today. Okay, so there is a mistake in the question. It's not output value, it should be input values. What will the prediction if the anyway, prediction meaning we are trying to predict the output values. So given value to us should be input. So given input values are 0.51 or 0.49 in both scenario, what will the corresponding output value? So the equation we came up with is x1 minus 0.5 greater than 0. So we'll make the decision based on this equation. In first scenario, the input is 0.51 minus 0.5. It's greater than 0. So the output class will be, in this case, will be 1. Other case, it's 0.49 minus 0.5 greater than 0. So this is false. So output class will be here 0. Did you get this question properly? What it is asking? We have a
Yes, sir.
single neuron. Okay, good. We have a single neuron. We have a bias term. We have a W, and two input values are given to us, and we know the equation of W xi. You put everything. Input xi's are given. W is given. These xis are for two different instances, not single input. There is only one input. So one time only we can give one input. One input is given to us, corresponding W, corresponding bias is given. We know the decision boundary, then decide. It's this decision boundary holds, class 1, otherwise. Okay, one last question. Identify the statements that are true about the learning algorithm. So kind of the basic learning algorithm concept we started. What's the which statement is true regarding that? Let's see the statements. First, it says maximize the objective function. So, so the flaw with this statement is we don't always maximize the objective function. The perfect statement is optimizing the objective function. Optimization, it can be either maximization or the minimization. If it is a objective function is kind of loss, and the nature of the objective function is a loss function, then we have to minimize it. If the nature of the objective function is like kind of find similarity or kind of find closeness, there we have to maximize. So again, different objective functions we will also see through this course. So statement one is not correct. It's not like maximizing the objective function. The perfect statement is optimizing.
Objective function is like fx.
Objective function is the loss function we studied, the squared loss function.
Okay.
So we are achieving that objective through fx. But what is our goal to achieve? We have to minimize that objective function, meaning that squared loss we calculated that should be as close to zero as possible. Right? So that is our objective. The loss value should be as close to zero as possible. Optimizing objective function.
Objective function can be any other function also, no? Yeah, only loss
It can be
function.
any other function. Now, till now, we have studied only squared loss. It can be any other function also, any other loss function. We'll see varieties of objective function through this course. There are some 12, 13 lectures. So all these things we are studying till now, it's like just to get started with. Everything has different variations like objective function. Then this fx we are studying only sigma now. Different fx we'll study. Different network architecture we'll study. Different input outputs we'll study. Input output pairs. So all the variations we'll study. But till now, just make sure you're understanding the basic things. What is objective function? What is loss function? What is gradient descent? Like how what's the mean of what do we mean by learning a model, like instead of learning these w values, the basic things if you can understand, then we can quickly go to the major concepts. Okay, so going to the second statement, launch the parameter from the data. Yeah, parameter again, parameter maybe the first time we are hearing. The parameter is that model w values, they are called the parameters. So that's our goal from the learning algorithm. You have to learn the optimal W values given determining X and Y pair. Right. So second statement is valid.
So
Okay.
you are saying parameters are the weights we give
Parameters are
to.
the weights. Yeah. So weights. Then you can say model, learning a model, meaning learning those weights or the parameters. These are kind of synonymous terms. Model is just not the parameter. Model has multiple things. When we say model, it comprises of weights or parameters plus the objective function. Mm, yeah, these two majorly, these two things. It is combination of both weights and what is the objective function. There is some other concept like what is the kind of activation function in the hidden layer that we'll study in the upcoming lectures. Till now, you have only learned what are parameters, what are objective function, what is model, and what is like how after we have done the aggregation in the perceptron, how do we pass the information to the next neuron, and that is through another function. So that is called the activation function. Again, in detail we'll study. So when I said
So like
activation function,
yeah, so objective function is to like a function created to achieve some objective, and
yes,
activation function is the function that defines when it will be activated. That's it.
yeah, perfectly fine. When this neuron will be fired or activated, that is decided through this function that is called activation function. Objective function is we have to come up with these W values that will help us to minimize the loss between uh, input X and oh, somehow it's not input X and predicted Y. It's not input X and input Y. Carefully look at it. It's input X and predicted. Sorry. It's not input X. This is input Y and predicted Y. So that is the objective function. So objective function will like kind of minimize the difference between these two. input y and the predicted y. So if input y had only, let's say there are four inputs and they were 0, 0, 1, 0 like this. Predicted y should be 0, 0, 1, 0. That's our goal. If it predicts like 0, 1, 1, 0, then there is one loss happened, right? We have to minimize that loss.
But we always input X, na? We don't input Y.
No. We input x to the model, but we compare with y every time. The loss is always compared with y. We giving input x, we predicted this y hat, right?
Yeah.
Through this model, we compare with what is the actual y. Our goal is to, our prediction should be as close to as the actual y. This ya is the actual y, ya hat is the predicted y.
Okay. Okay.
So that is the objective. The actual y and the predicted y, they should be as close to as possible.
Yeah. Thank you.
Okay, so I think I covered a few of the questions. We have 20 minutes around for the lecture to be over. If you have any doubt, ask.
Yeah, if you have time, you said you'll explain that
Okay.
difference.
Okay, differentiation. So let me think. What I wanted to explain. Okay. So what is this delta WT we saw here? We know delta WT is del L WB by del W, right? So when the differentiation, what do we mean by differentiation? So we're differentiating a function. Here L is a function. Function, when we are saying something is function, it has some input parameter. Here it is a function of W and B. So the value of L can change with some change in value of W or B, right? Or B meaning both will change, L will change, either of them will change, L will also change. Can change, not will change, can change. So if it is a function of some like kind of some parameter that we can plot, let's say, let's consider L is only the function of W, right? That I'm plotting here. With change in W, how L will change. The nature here, the curve can be anything, right? I'm plotting just one curve here. Maybe this curve can be also like this also, or like this. So this nature of this input Y, sorry, W and L can be anything that we don't know yet, right? That will depend on the XY pair and the current W value. Depending on that, the nature of the plot will be decided, right? So here what happens, you change W, like here W is, let's say at one time point W is this, and another time point W is this, W T plus 1. That's it. So correspondingly, you can see the loss values, right? Here a loss is L1, let's say this is loss is L2. And you can clearly see here the loss value in L2 is higher than L1. Our goal is come, we should given these two W values, which W will choose? We'll choose the W at WT. This is there is no significance of T or T plus 1. You can just consider two different parameters, because here the corresponding loss value L1 is lower as compared to L2, right? So when we say differentiation, what we see, like with small change in W, this can be explained in a way that if you change W to W plus delta W, so this delta W can be as close to as zero. That we call, there is a term that is infinitesimally small, right? Very small. You make very small change in W value, how much change you are seeing in the L value, that is the differences. So there will be some change in the L value. So when the W value, so I'm plotting a table here. When the W value was W, actually W, let's say this is capital W and capital L, and the loss value was, let's say, small l. You change it to W plus delta W, very small change, maybe 0.00001, some very small change. And how much L is changing? That is the value of differences. That's what we want to capture. If this is a flattened curve, this relationship between W and L is completely flattened at this region. You make any change in W, the L is stagnant. The delta will be zero. Right? So here we cannot do anything. Like we are stuck at that point. So here the differentiation value is zero. So our goal is to get this delta WT values to like as close to as zero as possible. And if we are stuck at this region, here also delta WT value will be zero. But this is a bad region. Like this kind of region we don't know. No, don't want to achieve. We want to achieve. We want to reach this point where also the delta W value is zero. And how to get rid of these things, we'll go discuss these things further. I'm just for the sake of understanding differentiation, I'm explaining. So these are the points where the delta WT is zero, and these are the points. Let's say there are some significant values. The way we discussed here, we change from WT to WT plus one, and there is some delta L here, right? So let's say this is very small WT to WT plus one. I am just
Oh.
magnified it. Mhm.
Aha.
Yeah. So just imagine I have magnified this scale. The change actually is very small. So with this change, how much L is changing? That will be represented by this del WT. Okay? That is the differentiation. But how do we compute it? This is for understanding. This is the concept. How do we compute it? We know L is a function of W and B. So what is L here? For our case, this is summation of I yi hat minus y whole square. Y is a fixed number that is given to us, whether every point has 0 or 1 value corresponding to y. But y hat, what is y hat? We know y hat is 1 by 1 plus e to the power minus w transpose x plus b. If you forget b, it is, let's say I'm ignoring b, just for sake of simplicity, it is 1 plus 1 by 1 plus e to the minus w transpose x, right? So definitely L has, if we expand like replace this value here, L has the w component. So in terms of w, how what we can write L equal to summation of I 1 by 1 plus e to the power minus wx minus y whole square, right? Now you take the partial differentiation. Why partial differentiation? Partial differentiation of del L by del W. Because there are many other parameters possibly that will be involved. Let's say in this case, B is also involved. If let's say here B was there, imagine B was there. There are two parameters involved, B and W, right? We are only differentiating here with respect to one parameter. That's why we are saying partial differentiation. If only one parameter is involved, we can call this as full differentiation. Like no need to call this as partial differentiation. When we are doing partial differentiation, what happens? Whatever changes in B, that doesn't affect. We are not concerned about the changes in B. We are only concerned about the changes in W. What will happen to the last value if we change in W value with very small delta W, right? So how do we compute it? There are formulas like for let's say this is if L equal to let's say W square, for sake of understanding I'm saying, what will be del L by del W? It will be 2 into W. Like the formula is if L equal to W to the power n, it will be n into n minus 1. So n into W, right? NW into n minus 1. What I'm saying? NW into n minus 1 to the power n minus 1. So there are different equations for differentiation. Let's say L equal to e to the power W. Then del L by del W will be same e to the power W. So how we are getting these values? W square is when we are partially differentiating W square, we are getting 2W. Again, what does this mean? Like with unit change in W, with unit change meaning, let's say delta W we added or subtracted, how much change happening to this L value? That is 2 into delta L. That's why we're saying this is 2 W. So you can take a plot or table for x and y, let's say is x square. So for 1 it is 1, for 2 it is 4, for 3 it is 9, and you try to change some the value of x a little bit and see how much the value of y is changing. Then we can you can understand why it is 2W. Sorry, right?
Example that you are giving.
Meaning you can imagine right here, like if I'm changing from 1 to 1.2, so what will be the value of y here, and how this change and the change happened here, they are related,
So this
right?
example of x and y you are giving here, it is dy by dx, differentiation of y with
Yes,
respect to x.
yeah, it is dy by dx here. So we
Okay.
are discussing del L by del W. And
Yeah,
that's
so
the
this is very helpful. Thank you. I just have now one query. Like this sort of mathematical questions will be there, like they can be asked.
not these kind of questions generally in NPTEL. The questions are conceptual in nature. You can see the kind of questions I'm discussing. They just require your, if you have gone through the lectures, you understand the concepts, you can answer them clearly. I think this was taught in the lecture. Again, these all these things are very conceptual questions. I have not solved any mathematical questions yet. To
No,
explain the
I am
material, I am
asking,
explaining the mathematics, but solving the
yeah, I am
question.
asking like we should go still deeper into differentiation or this much knowledge will be enough.
Again, what is your target? If you want to like work in the area like machine learning area deeply for some rigor work, then you have to understand this differentiation more thoroughly. If you want to just use some packages, then do some tasks for fun purposes, then no need to do.
Okay, thank you.
Because these things you will not be using very explicitly, but understanding these things will help you to decide what loss function I will use, what will be the activation function, what will be the number of layers, number of parameters. They are kind of intuition building elements that will help you to decide or intuitively design something, come up with some design choice while modeling. But if you want to just understand and try out for time pass or something, just use the API. It's fine. Like no need to go that deep.
Thank you.
Any other doubt? Um, 5 more minutes. Otherwise, we'll stop the session.
Excuse me, sir.
Yeah.
Whatever question you have solved, that is related to this topic or related to the assignment also?
What are questions?
No, whatever, like right now you multiple choice question, right? So
Mhm.
multiple MCQ question. So that is
Mhm.
related to this topic, particular topic, or related to our assignment also. That is main.
Your assignment also.
Okay, sir.
And then week one assignment that was there. will those questions be discussed like they'll be discussed after the submission date is over or something?
If you, I don't know when the weekend results are published. Once
Not
they're
the results,
published,
not the results, but the submission date is like 7th August. So
okay,
after,
after submission data, I can discuss.
okay,
You can let me know ki when the week's submission date is over. I will discuss the questions if you want me.
oh,
I will also take a look at what are the submission dates.
Yes, sir.
Okay. Any other doubt? Okay. So if there are no more doubts, we can close the session. Thanks for joining.
thank you.
Thank you, sir.
Thank you.
Yeah.